Welcome to today's session. In this video, we'll be tackling LeetCode problem number 45, Jump Game 2. This is a popular dynamic programming and greedy algorithm problem that challenges us to determine the minimum number of jumps needed to reach the end of an array. Stick around as we explore an efficient approach to solve this problem step by step. Let's dive in. In this problem, you're provided with an integer array nums, where each element in the array represents the maximum number of steps you can take forward from that position. The task is to determine the minimum number of jumps required to reach the last index of the array. You can safely assume that it is always possible to reach the last index. For the input, nums is an array of integers where the length of the array, n, ranges from 1 to 10,000, and each element in the array is between 0 and 1,000. The output will be an integer representing the minimum jumps needed to complete the task. Let's explore some examples to see how this works in practice. In the first example, the input array is nums equals 2, 3, 1, 1, 4. The output is 2, and here's why. Starting at index 0, the value is 2, which means you can jump up to 2 steps forward. In this case, you jump to index 1, where the value is 3. From index 1, you can jump up to 3 steps forward. You then jump directly to index 4, which is the last index. This requires a total of 2 jumps. In the second example, the input array is nums equals 2, 3, 0, 1, 4. Again, the output is 2. Starting at index 0, you jump to index 1, where the value is 3. From index 1, you can jump directly to the last index, index 4. The number of jumps remains 2. Now, consider the third example, where the input is nums equals 1, 2, 3. The output is also 2. Starting at index 0, the value is 1, so you can only jump to index 1. From index 1, the value is 2, allowing you to jump to index 2, which is the last index. This results in a total of 2 jumps. Keep in mind the constraints of the problem. The length of the array, nums.length, can go up to 10,000, and the values within the array are between 0 and 1,000. With these constraints, the problem guarantees that reaching the last index is always possible. It's important to consider some edge cases to fully understand the problem. For a single element array like nums equals 0, the output is 0 because you're already at the last index and no jumps are needed. If all the elements are 1s, such as nums equals 1, 1, 1, 1, the output is n1, as you must make 1 jump at a time to reach the end. On the other hand, if the first element has the maximum jump value, like in nums equals 1000, 1, 1, 1, with a length of 10,000, the output is 1 because you can directly jump to the last index from the first position. These scenarios highlight the need to carefully evaluate the array structure to determine the minimum jumps efficiently. To solve the Jump Game 2 problem, our goal is to minimize the number of jumps required to reach the last index of the array. Let's first consider the brute force approach using recursive backtracking. The intuition here is fairly straightforward. From each index, we attempt all possible jumps within the range of 1 to nums I, where nums I is the maximum jump length from that position. By recursively calculating the minimum jumps for all possible paths, we can identify the optimal solution. However, this approach has a significant drawback. Since it explores all possible jump sequences, it results in repeated calculations for overlapping subproblems, leading to exponential time complexity, specifically n to the power of n, which is highly inefficient for larger inputs. Now, an improved method is the dynamic programming approach using tabulation. Here, we maintain an array dp where each entry dp, I, represents the minimum number of jumps needed to reach index I. By iterating through all prior indices j and checking if we can reach I from j, we update the value of dp, I, as dp, j, plus 1. This approach systematically builds the solution iteratively, avoiding redundant calculations. The dynamic programming approach has some key advantages. By iteratively building the solution, we avoid the inefficiencies of backtracking. However, the main challenge lies in the nested loops. For each index I, we must iterate over all prior indices j to determine the minimum jumps. This increases the time complexity to n squared, where the outer loop runs once for every index, and the inner loop processes all indices up to the current one. To address this inefficiency, we can turn to the optimized greedy approach. The greedy method eliminates the need for nested loops by leveraging two key variables, farthest, which tracks the furthest position reachable at any point, and current_jump_end, which defines the boundary of the current jump. Each time we exceed this boundary, we increment the jump count and extend the boundary to farthest. The essential idea is that the minimum number of jumps is determined by how far we can extend the boundary with each jump. By processing the array in a single pass and making constant time updates per index, this approach achieves a much more efficient O(n) time complexity. After evaluating the different approaches, we chose the optimized greedy strategy due to its simplicity and efficiency. The problem specifically asks for the minimum number of jumps, not all possible paths, making the greedy approach a perfect fit. It directly minimizes jumps without unnecessary calculations, achieving O(n) time complexity, which is well suited for the problem's constraints. However, there are trade-offs to consider. While greedy is ideal for this task, it is less suitable for scenarios where tracking all possible paths is required, as in more complex variants of the problem. Dynamic programming, by contrast, is more generalizable but slower, with an O(n)² complexity and additional overhead. The greedy method offers key insights. We only need to track the farthest reachable position and the number of jumps. The current_jump_end variable helps us determine when to increment the jump count, acting as a boundary for each jump. This approach is not only optimal in time complexity but also elegant in its minimal space usage, requiring O(1) extra space. It effectively handles edge cases like small arrays or scenarios with large jumps, making it robust and reliable for this problem. In this problem, we are tasked with finding the minimum number of jumps required to reach the last index of an array. Each element in the array represents the maximum number of steps you can take forward from that position. To solve this, we use a greedy approach. The idea is to minimize the number of jumps while ensuring that we never exceed the bounds of the array. The algorithm starts by initializing three variables. First, jumps, which will keep track of the total number of jumps made. Next is current_end, which marks the furthest index we can reach within the current jump. Finally, we have farthest, which keeps track of the maximum index we can reach at any given point in the iteration. These variables will help us manage the jumping process efficiently as we traverse the array. Now, to implement the greedy approach, we iterate through the array using a for loop, stopping at the second to last index because once we jump to the last index, the problem is solved. At each index, we compute the furthest point that can be reached by updating farthest to the maximum of its current value and I plus nums, I. This tells us the furthest we can go from the current position. If the current index matches current_end, it means we've reached the limit of our current jump. At this point, we increment the jumps counter and update current_end to farthest, effectively starting a new jump. Additionally, we handle the edge case where the input array has only one element. In that case, no jumps are needed, so we return 0. Finally, after the loop finishes, the value of jumps will represent the minimum number of jumps required to reach the last index. The greedy approach is effective because it ensures that each jump covers the largest possible distance, minimizing the total number of jumps. The current_end variable plays a critical role here, as it guarantees that decisions about making the next jump are only taken at the right points. By stopping the loop at len nums 2, we avoid redundant checks once we know we can reach the last index. This method is also efficient in terms of space and time complexity. The algorithm has a time complexity of O(n), as we only iterate through the array once. Its space complexity is O(1), since we only use three integer variables, jumps, current_end, and farthest, to track the state throughout the computation. No additional data structures are required, making this approach both time-efficient and space-efficient. Let's walk through a complete example to understand how the algorithm works in practice. Consider the input nums equals 2, 3, 1, 1, 4. We start by initializing our variables, jumps equals 0, current_end equals 0, and farthest equals 0. As we iterate through the array, at index 0, we calculate farthest as the maximum of 0 and 0 plus nums, 0, which is 2. Since the current index matches current_end, 0 equals 0, we increment jumps to 1 and update current_end to 2. Moving to index 1, we update farthest again. it becomes the maximum of 2 and 1 plus nums, 1, which is 4. At index 2, farthest remains 4, as 2 plus nums, 2, does not exceed it. When we reach the end of the current jumps range at index 2, we increment jumps to 2 and update current_n to 4. At this point, we've met or exceeded the last index, so the process terminates. With the termination of the loop, we can confidently return the result, which is jumps equals 2. This means that it takes a minimum of 2 jumps to reach the last index of the array. The example output is 2. Now, let's briefly consider some edge cases. If the input has only one element, such as 0, no jumps are needed, so the output is 0. For arrays with large maximum values, such as 10 to the power of 4, 1, 1, 1, the greedy approach ensures that we always make optimal jumps without being affected by the size of the numbers. Finally, the problem guarantees that the last index is always reachable, so we don't need to handle cases where reaching the end is impossible, such as 3, 2, 1, 0, 4. These considerations make the solution robust and reliable for all valid inputs. The algorithm is already optimized for efficiency, avoiding unnecessary recursive calls or the use of dynamic programming. By leveraging a greedy approach, we focus on making locally optimal decisions at each step, which leads to a globally optimal solution. This eliminates the need to explore all possible paths, reducing both computation time and memory usage. The simplicity of using just 3 integer variables, jumps, current_n, and farthest, ensures that the solution is not only fast but also highly space efficient. This combination of speed and minimal memory usage highlights the strength of the greedy approach for solving this problem. The solution implements a greedy approach to solve the jump game 2 problem efficiently. The goal is to find the minimum number of jumps required to reach the end of the array. We start by initializing 3 variables. 1. Jumps to count the number of jumps made. 2. Current_n to track the farthest point we can reach with the current number of jumps. 3. Farthest to track the farthest point we can potentially reach from the current position. The loop iterates through the array up to n1, excluding the last index since we don't need to jump if we're already there. For each index I, we calculate how far we can reach, I plus nums, I, and update the farthest variable accordingly. If the current index I reaches current_n, it means we've used up all the steps in our current jump. At this point, we increment the jumps counter and update current_n to farthest, effectively making a jump to the farthest point we can reach. The loop breaks early if current_n reaches or exceeds the last index, n1, since we don't need further jumps. This greedy approach ensures that we minimize the number of jumps by always jumping to the farthest reachable position. The time complexity is O(n), because we iterate through the array once, and the space complexity is O(1), as no additional data structures are used. Here, we begin by defining the solution class and implementing the jump method, which takes an array of integers called nums. The goal is to determine the minimum number of jumps needed to reach the last index of the array. First, we check if the array length is 1 or less, in which case no jumps are needed, so we return 0. Next, we initialize 3 variables, jumps to count the number of jumps, current_n to mark the end of the current jump range, and farthest to track the farthest index we can reach during this process. Then, we use a for loop to iterate through the array, stopping one step before the last index since reaching the last index is our goal. Inside the loop, we update farthest to the maximum of its current value and the sum of the current index and the jump length at that index. This ensures that we're calculating the farthest point we can reach from the current position. If the current index matches current end, it means we've reached the limit of our current jump range, so we increment the jumps counter and update current end to the value of farthest. If, at this point, current end reaches or surpasses the last index, we know we can stop further processing since the target is reachable. Finally, after exiting the loop, we return the total number of jumps. This ensures that the method outputs the minimum number of jumps required to reach the last index. The implementation is efficient, as it only requires one pass through the array, making it an O(n) solution. This approach leverages the greedy algorithm by always trying to jump to the farthest point possible at each step, ensuring that we minimize the overall number of jumps. With this, we complete the Java implementation for the Jump Game 2 problem. In this problem, we are tasked with finding the minimum number of jumps needed to reach the last index of an array. Each value in the array represents the maximum number of steps you can jump forward from that index. For example, in the array nums equals 2, 3, 1, 1, 4, the value at index 0 is 2, meaning you can jump up to 2 steps forward from there. The goal is to determine the smallest number of jumps required to reach the last index, starting from the first index. Let's explore how to solve this problem step by step. To solve this, we initialize 3 variables: jumps to track the number of jumps taken, current_n to represent the farthest index we can reach with the current jump, and farthest to track the farthest index we can reach overall. Starting at index 0, we calculate farthest as the maximum of its current value and the sum of the current index and the value at that index. Here, farthest becomes 2 since max, 0, 0 plus 2, equals 2. Because we've reached the end of our current jump range, I equals current_end, we increment the jumps counter to 1 and update current_n to the value of farthest, which is now 2. Continuing, at index 1, we recalculate farthest as the maximum of its current value and 1 plus 3, which gives farthest equals 4. Since index 1 is not the end of our current range, no other updates are made yet. At index 2, we again update farthest as the maximum of its current value and 2 plus 1, which remains 4. Since we've now reached the end of the current jump range, I equals current_end, we increment the jumps counter to 2 and set current_n to the value of farthest, which is 4. At this point, current_n is greater than or equal to the last index of the array, so we stop. The minimum number of jumps required to reach the last index for this example is 2. In the next example, nums equals 2, 3, 0, 1, 4, we follow the same approach. First, we initialize jumps, current_n, and farthest to 0. At index 0, we calculate farthest as max, 0, 0 plus 2, equals 2. Since we've reached the current jump range, I equals current_end, we increment jumps to 1 and update current_n to 2. Moving to index 1, we calculate farthest as max, 2, 1 plus 3, equals 4. However, since index 1 is not the end of the current jump range, no further updates are made yet. At index 2, we calculate farthest as max, 4, 2 plus 0, which remains 4. Because we've reached the end of the current jump range, I equals current_end, we increment the jumps counter to 2 and update current_n to 4. At this point, current_n is greater than or equal to the last index of the array, so we stop. The minimum number of jumps required for this example is also 2. Now, let's consider the example nums equals 1, 2, 3, 4, 5. As before, we start by initializing jumps, current_n, and farthest to 0. At index 0, we calculate farthest as max, 0, 0 plus 1, equals 1. Since we've reached the end of the current jump range, I equals current_n, we increment jumps to 1 and update current_n to 1. Next, at index 1, we calculate farthest as max, 1, 1 plus 2, equals 3. Again, since index 1 marks the end of the current jump range, we increment jumps to 2 and update current_n to 3. At index 2, we calculate farthest as max, 3, 2 plus 3, equals 5. Since we've reached the end of the current jump range, I equals current_n, we increment jumps to 3 and update current_n to 5. At this point, current_n is greater than or equal to the last index of the array, so we stop. For this example, the minimum number of jumps required to reach the last index is 3. Now, let's analyze the time complexity of our solution for jump game 2. The algorithm operates in O(n) time, where n is the length of the input array nums. To break this down, the outer loop iterates from index 0 to n2. This means we examine each element in the array exactly once, which directly contributes to the O(n) complexity. Within the loop, all operations are constant time. For instance, updating farthest with the maximum of its current value and I plus nums, I, is an O(1) operation. Similarly, checking whether I equals current_n and updating jumps or current_n are all O(1) operations as well. Since the loop runs n times and each iteration involves only constant time operations, the total time complexity of the algorithm remains O(n). Next, let's examine the best, average, and worst-case scenarios for this solution. In the best case, the input array allows us to reach the last index in just one jump, such as nums equals n1. Even here, the algorithm still iterates through the entire array, resulting in a time complexity of O(n). In the worst case, the array forces us to take one jump per element, as in nums equals 1, 1, 1. Again, the loop iterates over all elements, so the time complexity remains O(n). Whether it's the best, average, or worst case, the algorithm always processes the array linearly, ensuring the time complexity is consistently O(n). For space complexity, the solution is highly efficient, as it requires only a fixed number of variables such as jumps, current_end, and farthest, regardless of the input size. No additional data structures are used, so the space complexity is O(1), or constant space. Finally, let's compare the greedy solution to a brute force approach. A naive method would involve exploring all possible jump sequences from the first index to the last, calculating the minimum jumps for each path. This brute force approach has exponential time complexity, O(2 to the power of n) in the worst case, as it examines every possible combination of jumps. With memoization, we could reduce it to O(n², but it's still far less efficient than the greedy algorithm. By contrast, the greedy approach leverages the guarantee of a solution and focuses on reaching the farthest point with minimal jumps. This strategy reduces the time complexity to O(n) by making a single pass through the array and updating the jump count only when necessary. This makes the greedy algorithm both time and space efficient, making it the optimal solution for jump game 2. Mathematically, the algorithm processes each of the n elements exactly once and performs a constant number of operations per element. This gives us a total of n*(O1), which simplifies to O(n). Additionally, since no extra memory scales with input size, the space complexity is O(1). When solving jump game 2, there are a few common mistakes that can make your solution inefficient or incorrect. First, one frequent error is assuming that selecting the farthest reachable index at every step is always the best move. While it might seem optimal, this greedy choice can lead to suboptimal paths, as it doesn't account for maximizing the reach within the current step range. Instead, it's better to evaluate all possible jumps within the range and choose the one that extends your reach the most. Another mistake is relying on brute force, such as recursive backtracking, to explore every possible jump. This approach quickly becomes infeasible as the input size grows, with a time complexity of O(2 to the power of n). For instance, if n is 10,000, this method would take an astronomical amount of time to complete. Lastly, it's important to account for edge cases. For example, a single element array like 0 should immediately return 0 jumps, while an array like 1, 0, 2 should correctly indicate that no valid path exists. Ignoring these scenarios can lead to runtime errors or incorrect results, so always test against edge cases during development. Now, another challenge arises when input constraints are misunderstood. Some might assume the array could contain negative numbers or be unsorted, but the problem guarantees non-negative integers and valid paths. Overcomplicating the logic to handle scenarios that won't occur wastes valuable time during interviews or competitive programming. Additionally, inefficient tracking of jump ranges can significantly slow down your solution. For instance, repeatedly recalculating the reachable range instead of maintaining it dynamically can push your solution's complexity toward O(n²). To handle these issues effectively, it's essential to adopt a greedy approach. By tracking the current jump range and the farthest reachable index, you avoid redundant calculations, achieving an optimal O(n) runtime. During interviews, it's helpful to articulate the trade-offs between brute force and a greedy strategy. Focus on minimizing the number of jumps rather than the exact path, as this is the primary goal. Finally, keep in mind that jump game 2 is fundamentally a range coverage problem, which connects to many other interval-based questions. Recognizing this pattern will help you solve similar problems more efficiently. Speaking of related problems, understanding jump game 2 can help you tackle others with similar patterns. For example, LeetCode number 55, Jump Game, asks whether you can reach the last index at all, making it a simpler variant of this problem. Another example is LeetCode number 1024, Video Stitching, which involves covering intervals using a greedy strategy. Similarly, LeetCode number 134, gas station, and LeetCode number 435, non-overlapping intervals, both focus on applying greedy techniques to optimize solutions. Apart from greedy methods, there are alternative approaches to consider. Brute force, through recursive backtracking, is conceptually simple but highly inefficient, with a time complexity of O(2 to the power of n). It's mostly suitable for small inputs or as a way to understand the problem better. Dynamic programming is another option, where you solve subproblems to build the solution. While it guarantees correctness and has a time complexity of O(n²), it's slower than the greedy approach. Still, it can be a useful technique for verifying your solution or deepening your understanding of the problem. Among the various approaches, the greedy strategy stands out as the most optimal for Jump Game 2. It runs in linear time, O(n), making it the best choice for competitive programming and interview scenarios. However, implementing it requires careful planning to ensure that you're dynamically updating the current jump range and accurately tracking the farthest reachable index. By doing so, you minimize redundant computations and ensure that your solution efficiently handles even the largest inputs. This balance of efficiency and clarity is why the greedy approach is the preferred method for solving this problem. Great job following along. To summarize, we solved the Jump Game 2 problem using a greedy algorithm, achieving O(n) time complexity and O(1) space complexity. Remember, greedy strategies are powerful for optimization problems like this one. Thanks for watching, and be sure to like, subscribe, and stay tuned for more coding tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!